And now, please welcome Nathan Ashcraft.
All right, thanks. All right, well, I didn't know mining wastewater had such emotions, but that was a good way to introduce what we're doing here. So a news article this summer said tailings ponds are the biggest environmental disaster you've never heard of. And I assume that's the case for many of you. So I'm going to lay out first what a tailings pond is, the water from a mining operation, and then how we can eliminate it, and how that provides benefit to mining companies and the environment. So first, a representative mining operation. In the top left, rock is dug out of a pit, and then the good stuff, the product, has to be separated from the bad stuff, the waste rock and clay. And typically how that's done is that material that you see is crushed into small pieces, water is added to it to become a slurry, the product is separated from the waste, and then the waste material is stored in what is called a tailings pond. And it's a bit of a misnomer because these are giant lakes, as you'll see. So we're going to be highlighting here the tailings pond in the bottom left, the waste rock, which is also typically an output of the operation, and then the fresh water that goes into the site. We're going to show you how you can eliminate all three of those to create a sustainable mining operation. So just to even set the stage on what mining is used for, it's a huge driver of agricultural industry. Phosphate and potassium, or potash, are derived from mining. A lot of our construction, automotive, comes from materials that are mined. It has a huge impact on energy applications, from coal to uranium to silica, which is being used for frac sand in the US, to materials that just have a variety of uses in electronics and other applications you can see there in the middle. In the US, there's over 7,000 mining operations, and a significant portion of those have large tailings ponds that need addressed. These ponds can be over 1 billion gallons in size, and that probably doesn't mean anything to you. It's tough to get your head around. So a couple comparisons, that's over 10,000 Olympic-sized swimming pools in one feature, or over 300 Dallas Cowboys stadiums full of tailings. So that's the size that some of these structures can be. Here's just a picture of one of these ponds. They've taken a valley, dammed it down the middle, and put their wastewater here to settle for decades. That's the current technology of how to treat this wastewater, is just to let it sit there. Here's another shot from Central Florida, where there's been a lot of phosphate mining over the last century. If you see those lakes in the red circle, those are tailings ponds from phosphate mining operations there. So these are big, they take up lots of areas, they disrupt the environment, and they're a very inefficient use of water. A few other stories from this summer. They're expensive to clean up. So this is just a standard mine that closed up shop. They're estimating it takes $200 million to clean up the tailings pond from that site. The slide that I led off with about the environmental disaster was a mine in Canada that ruptured and leaked 25 million cubic meters of wastewater. It contaminated 2 lakes, a river, decimated a large area of forest land as well. So this provides some difficulties for the mine operator. A lot of times sites have to close up because of the liability with these. And as a follow-on, regulation in this industry is getting more stringent, not less stringent, because of environmental impacts. So why are these so challenging? Why can't they be treated like other wastewater streams? It's really a combination of 2 things. One, the massive scale of the problem. The amount of wastewater generated by these sites is enormous. And what you're trying to remove is very fine particulate matter. So I've shown that in the bottom there, illustrating it by clay particles that get dispersed. This material almost can look like coffee. And so you can imagine, how do you separate the particles out of your coffee? It further complicates that these materials often have the same surface charge, so they electrostatically repel one another. So it's a further difficulty in trying to consolidate this material out and leave reclaimed water. So in general, I've been laying the stage that these are unsustainable operations. They disrupt large areas of the environment. They can limit the lifetime of a mine. They're a very inefficient use of water. There's also additional liabilities, regulations, and just negative PR that comes with operating these and associated issues. So some sites do use a partial treatment called thickening. They add a flocculant material that thickens or aggregates the fine particulates and turns it into a soupy material. You're able to reclaim a small portion of the water, but the rest of the material is still a fluid. It still goes into an impoundment. This is, at best, a partial solution. Our process, which we call ATA, that comes from the acronyms we've given to our polymer and the components, activator, tether, anchor, which showed up in the text messages between the tailings and the polymers, is illustrated here. So we take the tailing stream and split it into two. This is done simply with common equipment, into a finer fraction and a coarser fraction. The finer fraction, we put one polymer called the activator. It serves to aggregate that material. And on the coarser material, we put something called the tether polymer, which self-assembles onto that surface and functionalizes it to grab the activated fines. When these two materials are combined, they immediately stick together, forming a material that has high geotechnical strength and almost immediately on its own separates, leaving reclaimed water behind. So I'm going to show you what this looks like through a video. I think it really shows how quickly this process works. So on the left is the coarser tailing sample that we split apart, and we are adding our tether polymer to that. And what we've done here for the lab scale demonstration, we just shake that jar to allow the polymer to mix. In a real world setting, we would just be adding the polymer inline to this stream. So the residence time for this step is roughly 5 seconds, as you've seen here. So then we take the fine tailing stream in the middle jar. We add our activator polymer, as I showed on the previous slide. And again, this serves to aggregate that material and functionalize it to work with the tethered coarser particles. And same thing here. This is done in line, so the residence time is just a matter of seconds. And we've shaken it in the jar to represent pipe flow. So now these two separate streams are primed, and all we have to do is mix them together. As I've said, the coarse particles grab onto the fine particles, generating a geotechnically stable material. And as you'll see, once they're combined and mixed, that material rapidly settles. So we're taking something that on its own would take years, even decades to settle out, and making that happen in a matter of seconds. So again, about the same residence time as the individual polymer applications is all it takes for those the mixing to occur. And you'll be able to see even in here with suboptimal lighting, that solid material is separated and settling. And to show how easy it is to separate, we just pour that material onto a wire mesh screen. So we're not using any sort of fancy filtration or other equipment to do the separation. You can just pour the material onto a coarse mesh screen to do the separation. So all that water is immediately available for the mine site to reuse. And as we'll further show, we didn't just separate the solids, but we've turned them into a material that is geotechnically stable. And I keep saying that because the material is strong enough to actually go back into a mine pit. So a site can be reclaiming the land that they're disrupting during their operations as they go along. It's no longer something that has to be done at the end of the life of a mine. So to illustrate that, we'll show that this material has just been gravity filtered. We can pick that material up. It's clearly not a fluid. It doesn't move. And then to further demonstrate what this material would look like is it's put in a mine pit and has its own weight pressing upon it. We'll take a clump of that and just press it between paper towels to synthesize that compression. So that's what you'll see here. And then last, some treatments, the thickening that I talked about, again, those are a partial solution. What happens when that material flows or gets rained on? It disperses and can get back into the environment. Our material doesn't do that. So to demonstrate that, we'll take a piece of the material and throw it right back in water. So we've generated it, and then immediately we can throw it back in water, and it doesn't disperse. So you're not putting this material back into the environment anyway. It goes where you put it. When we made this video, we were able to show 5 weeks later, we've seen the same thing after 2 years. The material is incredibly stable. So this truly is a comprehensive solution. I'll show that it's cost effective when you look at the life cycle of a mine. I do want to highlight that we use non-toxic polymers. So there's an environmental friendly aspect to the actual chemicals themselves. It's broadly applicable to all the mining operations that I've talked about. It can be used to treat tailings as they're generated. It can also be used to reclaim existing tailings ponds from sites that have closed up shop. So this is a simple diagram of how the process works. Just like the video showed, the tailings can be split into a fine and coarse fraction. We add our activator to the fines, tether to the coarse, mix, and do the separation. Some sites conveniently have those two streams separate, so our implementation for those sites is as shown here. And so this approach, either splitting it or treating the two streams as they're generated separately, will account for almost all mining operations. So some of the advantages, obviously, compared to a tailings pond or even the thickening that I showed, is it's fast, it's done inline, so there's no need for a large storage area. The solids coming out can be directly stacked and put back into the mine pit, so you don't have any environmental disruption with a tailings pond. The water is immediately recovered, so that water can be used in a closed-loop fashion throughout the facility, minimizing the water that's taken in from either lakes or wells. The water that we generate is of high quality. It meets all the criteria that a site needs to be reused. And further, the equipment that's done that can be used to do this process is quite simple. So you'll see some of the economics are quite compelling from a capital cost perspective. Here's another example as applied to some phosphate tailings. As received tailings, split them, did our treatment in the middle, and again the same separation on the right. Here's a very apples to apples comparison with the best thickening approach out there. Our material shown on the left, thickening on the right. Our material is over 300 times stronger, so there's no means a fluid material. It's truly a solid. Maximal water recovery is achieved with our process. So getting to the economics, this is traditionally what a mine site looked at, is how much does it cost to do a treatment from a capital point of view and from an operating point of view. So you can see a tailings pond looks pretty nice from an operating point of view, as I've shown in the column on the right there in the dollar per ton of tailings treated. Thickening is a bit more. Our approach is just a little less than thickening, but still more than a tailings pond from an operating point of view. If you look at the capital cost, though, putting a tailings pond in place is expensive. It's a huge structure, it has to be well geoengineered, and these in some cases are even conservative costs. Thickening kind of is in the middle of the road, whereas I said with ours, the capital costs are quite low. If you look at the end of the life of a mine, what are the reclamation costs? This is where there's a huge benefit in our process. You don't have to spend hundreds of millions of dollars reclaiming your mine site, restoring it back to its original habitat. There's some other benefits on a site-by-site basis that I won't have time to go into now. But when you look at the cost of water, the cost of potentially adding additional capacity to your tailings pond through the operation of the life, or even the fact that a tailings pond could limit the overall lifetime of a site. These can be huge drivers for a site that's already in operation. So the status of the technology, we've demonstrated it at 2 pilot trials with the phosphate mine, a pilot and plant trial with the potash mine, also a pilot and full plant trial with the silica mine. And these have been done in partnership with these companies. So to summarize, We feel that when you look at the life cycle cost of a mine, this is by far the lowest cost treatment. It eliminates the tailings ponds and allows that water to be immediately reused. And we found that this approach, our materials and process, will have applications in other industries besides waste treatment. So we've worked with some companies that actually want their product material dewatered in certain applications. And last, I forgot to put on here, but we have issued patents in 6 countries and a bunch of follow-on patents coming as well. So this is a patented technology. So again, to wrap up, we're going to take this mining operation, we're going to eliminate their waste outputs, almost eliminate their need for continual fresh water, and at the same time reclaim their mine pit as they go along. I'd like to quickly highlight our approach is to license this technology to the end users. We come up with a value share approach. We look at how much value this approach is creating for a site and come up with an equitable split. A very small site with no additional benefits might be in the range of $1 million a year in value created for our license, where some of the larger sites could be in the 10 million range. Don't have time to talk about the team, but I do want to highlight that there really is a nice benefit to the prizes given here. As I said, all of our work to date has been done in partnership with mine sites. They've supplied the engineering time and equipment to do our trial work. And so with the prize money from Ocean Exchange, we'd be able to build our own trailer-mounted pilot unit that we could take from site to site. And so we think that this would really improve the rate of adoption of the technology if we were able to quickly bring that to a site and show off the technology. And so I just wanted to show a picture just so you can get a feel. This is not what we would build. This is a picture I found on the internet of a separate wastewater unit. But this is the scale of something that we would like to build ourselves so we could take it from site to site. There'd be a couple tanks for our polymers, a couple pumps, and a separator. And so this is one reason we're particularly excited about the opportunity to be here presenting to you all and competing for the prizes. So thank you so much for the opportunity. Thanks for the organizers for the chance to be here, and I'd be happy to take any questions you have.
Great job, Nathan. Question?
Several of these processing facilities will use other chemicals in their processing, arsenics and other polymers and so forth, that end up in the tailings and in the ponds. How does your polymer react to some of these other materials?
Yeah, that's a good question. So our polymer, we have yet to find a site where the water chemistry prohibits our process from working. And in fact, we've applied our treatment, as I mentioned, to some potash sites. They actually do their processing in fully saturated brine. So a gallon of their fluid, a third of that is actually dissolved salt. So that's like off the charts, contamination in a sense that could inhibit our polymers. But as far as other metals or heavy metals, they don't impact our process. We actually have additional polymers we can throw in to chelate those materials and remove them. But one other thing that's kind of a flip side of a question that we get a lot is, does your treatment leave residual polymers in the water that you recycle that would inhibit the mine operation? And we've done extensive third-party testing where we do a treatment in our lab, we send it out, have them tell us what's in the water. We've typically seen below 1 ppm of residual polymer. It typically just says like below detection limits. So we're not putting in residual water or residual polymers back into the process. It would inhibit how the mine does their processing. So that's another nice benefit of our two polymer approach. They pretty much, either one gets bound up in the solids that are removed.
Chuck's got a question over here.
Can you say a little bit more about how often is the mine compelled to deal with these tailings, or do they typically just let them sit there for 10 years? And because that was the lowest cost kind of method. And do you think this changes the game somehow, where they would want to deal with their tailings more often?
Can you summarize the question for him?
Yeah, so I think he's asking, maybe at what point would a company want to get involved with doing some sort of treatment to their tailings? Is that fair? So we found with current operating sites, it's typically somebody who's in a pinch. That means their tailings pond has filled up, but they're still planning to run for another decade. The cost of water has increased a lot, so the economics are different. Those have been really the big two immediate drivers, and those are for existing sites. For new sites or sites that are planning to expand, those would be an additional time where we would want to be in contact with them, because this does really revolutionize how they're thinking about running their site. They're no longer dealing with, waste material here, tailings pond here, piping in fresh water from a lake. So whenever there is a chance for, a significant plant upgrade, expansion, things like that would be another point where we would be involved with the site.
Any other questions? Here's one.
Very good presentation. I was just curious, are these polymers commercially available? Are there any regulatory issues associated with them? And have you looked at produced water? A huge problem with the fracking industry, so I was just curious about that.
Yeah. So these are polymers that we've developed. We have had them toll manufactured. So we're a small lab that's developed the technology. For our biggest plant trial, we had 60 tons of polymer toll manufactured for a 1-month trial, and that went fine. So we can source the material on huge volumes, volumes that sites would need. As far as regulatory issues, we haven't had any issues implementing this at any of the sites we've worked with. We went through reviews in several U.S. states and in Canada. And to your last point, we have looked at produced water, but produced water typically has several things wrong with it, and so you really need, this could potentially remove one part of, the problem with produced water, but wouldn't be a complete solution for that application, where this really is a complete solution for pretty much all mining companies.
One over here.
Yeah, just a quick question about, given the properties of the material that you're getting out of this, that it's dewatered to the point that it is, have you looked at alternative uses of this stuff as opposed to just sticking it back in the ground? I mean, look at things like fly ash and its incorporation in roadbed and all these other kind of things. Has there been any interest in doing something like that, or has anyone looked into that?
Yeah, so far the most kind of interest for a use of the material is for a mine site to use it on their property for building roads or other kind of landfill uses. It would be up to the site if they have a potential application of that material, whether it's a cement filler application like fly ash or maybe a construction material application. It's possible. That would really be up to the end user. It's possible they might not want to kind of engage in a new business like that, but at the very least they could use it on site for some beneficial uses, just besides filling in the mine pit.
And then Joan, another question.
So, are you likely to get any kind of bounce from the regulatory environment? That is, are there going to be stricter federal or state requirements for tailing ponds, how soon they have to be cleaned up, how limited they can be in capacity? Anything coming along that helps you?
Probably the biggest regulatory thing that's come along is in Canada. They've implemented a policy called Directive 87 that's targeted at the Canadian oil sands that tells the operators they have to treat a certain amount of their tailings to generate a solid of, it's a certain strength requirement. So I showed those strength numbers at 1 year and then at 5 years. We've shown that we can hit that 5-year strength mark within a week. So we think it's very compelling, but as far as I know, and I'm not a regulation expert, no operator in Canada has had their operations impacted or received a fine based on this regulation that was put out in 2011. So things are headed that way, but until those regulations are actually enforced in some capacity, we're not counting on that as a huge driver. But in general, things seem to be headed that way as far as more oversight rather than less.
Nathan, great job.
All right, thanks
Thank
a lot.
you. Appreciate it.